This sort of two-stage rocket, and that I'll be giving a talk on vortex rings till 4 o'clock, and then at 4:30 I'll show the second hour of absolute zero. So if any of you are interested in seeing the second hour, it'll be on at 4:30. In some sense, I'm here under false pretenses because this is a workshop for high Reynolds number turbulence, and I have worked in high Reynolds number turbulence all right, but the work is some years back, and my lab is now located in Trieste at ICTP. And I'd hoped that Joe Niemela would actually be here to give a talk to you this week about our experiments, which are now in very, very high Rayleigh numbers for convection, but in rotation. And but Joe is teaching now, and just can't get away to come here. So I'm very sorry that that won't happen. Instead, I'll talk about sort of the ultimate laminar flow, namely the propagation of vortex rings, which is a very interesting thing. I enjoy working on it very, very much because it's a very difficult topic. I'm a professor of low temperature physics, not a fluid dynamicist, but I love fluid dynamics, and this subject is difficult and demanding, and yet not terribly expensive to work on unless you have to have a PIB, which I don't. But at any rate, what I wanted to tell you about is work that I've been doing really since 2000, mostly with undergraduates. It's been very interesting that this is the sort of topic that you can actually profitably assign a very, very bright undergraduate. And in particular, Neil Sullivan was my undergraduate student for 4 years, and he's now finishing his PhD at Caltech, but he invented a lot of the techniques that I'm going to show you, and I think you realize that this is a very, very nice thing for undergraduates to work on. So the aim of this entire project is as follows. If you look up LAM, or any of the books on inviscid fluid mechanics, you can see the expression for the velocity of a vortex ring. It's the circulation divided by 4 pi times the radius of the ring, with a logarithmic correction, log 8r over a, and a is the core size, and beta is a vorticity structure factor. Depends on how you design the core, whether it's Gaussian or Rankine or any other kind of core, or hollow or whatever. And what is often done by my engineering colleagues is that they simply ignore the logarithmic factor here and make that a constant. And they ignore the fact that the radius may not be the radius of the gun, but so they simply make the radius equal to the radius of the gun, which is called R0 in this lecture. And they use something called the slug model, which suggests on good dimensional grounds that the circulation depends on the square of the stroke and divided by twice the time of the stroke. So having done that, you can do all sorts of dimensional analysis, and you can get very interesting, useful stuff that agrees well with, it agrees especially rather well with the propagation of rather vortex rings with fairly thick cores. Everything I say today has to do with a field I don't think anyone has worked on. These are vortex rings of very, very thin cores, typically 2 or 3% of the radius of the ring. So these are indeed extraordinarily thin vortices. The reason for that is that a lot of my expertise in quantum fluids has to do with propagation of vortex rings in superfluid helium, where the core is literally has a radius of 1 angstrom. So we have a lot of experience on those things. Actually, that problem is easier than this problem because, of course, here, what I want to talk about today, we have dissipation. So the question then is, how do you make vortex rings in water? Well, there are lots of designs of vortex guns, and lots of people have made them out of everything under the sun that'll make an impulsive motion of some smoke-filled air or dye-filled water. But here is an example of something I used for 5 or 6 years. Let's see. Yeah. The piston here is operated by a rack and pinion, and a motor drives this small gear and pushes the piston down as accurately as we can with linear velocity. Of course, it's really a trapezoidal waveform because you have to accelerate, you have to decelerate. But anyhow, what matters is the stroke length, which I call capital L, and the stroke time, which I call capital T. And with this particular gun, you can have strokes up to about 4 centimeters and stroke times from about 40 to 160 milliseconds. So they really go quite fast. How do we look at these things? Well, here's a picture of the gun on the left, and you can just see the electrode, which is used to make the visualization. The visualization is done by something, it's really an electrochemical technique called the Baker technique, because it was invented by a graduate student at Harvard quite a number of years ago. It's a very, very lovely technique because when I was a young man doing fluid mechanics, more than decades ago than I care to think, we used to put dye into these experiments. And of course what happens is you add dye, it changes the viscosity of the fluid, and you end up remeasuring the viscosity every hour or so because you've got so much gunk in the thing, and then after a while it just gets too colored to use. So this technique is very elegant. What you do is you take water and you add thymol blue, which is a pH indicator. And then you have an electrode in the mouth of the gun, and it's a cathode, and the anode is a rod on the periphery of the tank. Tank's typically that big around. And the diameter of the gun is an inch, 2.54 centimeters. And here's a picture from above of a ring propagating away. And here's a picture from the front of a ring which is deliberately set to be going very slowly. And what you see is that there is an instability to the core, which is very, very distinctive. It was first discovered by a German investigator called Crutch. And Crutch's article is very, very difficult to read. At least I took German, but boy, it's very high technical German, and I've had it translated, and I hope to get it published someplace because it's a very important pioneering paper. I don't know what happened to Crutch. His paper was published in 1939 from Berlin, and I suspect that wasn't a very safe place to be, 1939. The other thing you can see is there are really two kinds of ink. If you look here carefully, you can just see resolves of bubbles. And if you raise the potential between the cathode and anode above 2 volts, you start to electrolyze the water. And at the cathode, you get hydrogen bubbles. And of course, a vortex, by definition, has an enormous pressure gradient, and it sucks these bubbles right into the core. And seeing the bubbles here gives you sort of an impression of how really very, very small the core really is. What kind of things could we measure? Well, here is a picture of a vortex ring. I fired this ring from the gun with the electrochemical technique going, so the core was colored, and you can see the core here. It has a diameter 2A, and then you can see the core coming down here, and it has a diameter 2A. You can see that there is an ellipsoid around the whole thing. It's called the vortex bubble, and and you can see some smeared fluid back here. It's because I just fired that ring through a sheet of color, and so some of the stuff is coming off the back. Obviously, this bubble has an eccentricity. The radius of the ring is R. The radius of the bubble is R sub B, and the ratio between the two is called gamma. It's the eccentricity of this ellipse. You can understand the bubble if you could use an electromagnetic analogy. If you have a current loop in an external magnetic field, and you adjust things just right, there will be a region around the current loop, a spherical region, which just excludes all flux from the external magnet. And I find that analogy useful because the current density is analogous to the vorticity, and the external magnetic field B is analogous to the velocity of the ring in the lab system. So if you turn the external magnetic field off, the bubble disappears. And if you stop the ring, the bubble disappears. So, yeah, it disappears. You're doing a lot of things to the fluid too. But what happens in practice is when the thing reaches the far end of the tank, it sees its image and it expands in its image. And the bubble is no longer relevant. It's not the world's easiest thing to think about. Now, what I am aiming to do is to find a way to provide the same sets of formulas for propagation of a vortex ring in a viscous fluid as we have in the old books like Lamb for an inviscid fluid. And the question is, how can you make any progress in that particular direction? Well, we're very, very lucky that Phil Safman, who just died a few weeks ago, thought about this problem, and he considered a vorticity distribution in the core, which is given by the circulation divided by 4 pi nu. T nu is the kinematic viscosity, T the time since the experiment began, and this is the distribution of vorticity he begins with. He then gets a formula for the velocity of that ring in water, and by golly, it's exactly the same as the formula I showed you from Lamb, except that you can't approximate you can't neglect the logarithmic factor, because A is the square root of 4 nu times the time, and the vortex structure factor is known to be 0.558. And so you have to carry out all terms. Let me just remind you again. The core diameter is the square root of 4 times the kinematic viscosity times the time. The structure factor is 0.558. And the first very, very difficult problem we ran into is that the T that appears in the core size should be the elapsed time since the piston started to move. But it isn't. It is actually merely the stroke time. And once the ring detaches from the gun and starts to propagate across the tank, the vortex core no longer grows. And I know that to very high accuracy, and I'll show you how we determined that later on.
Has beta equal to a quarter.
Yeah, that's right. Then there's another one by Hicks, I think.
Yeah.
These are good 19th century fluid dynamicists who published these things. And Thomson, I guess, did the solid rotating core for his thesis, right. I think.
So the difference is that Safman assumed this Gaussian core.
Right. So now what you'd like to have is expressions for everything in that formula. You'd like to know the circulation. You'd like to know the radius of the thing. You'd like to know the eccentricity of the bubble and the effect of stroke time. And the question is, why would you want to know all those things? Well, because later on what we'd really like to be able to do is vortex-vortex interactions. In other words, we'd like to be able to do experiments, and we're sort of doing what nuclear physicists do scattering experiments. And so you'd really like to be able to develop a set of formula that you could use to do far, far more interesting things, namely things like collisions and reconnections and so on. So you have the bubble, which is an ellipsoid, but I just imagine that there must be a fictitious ellipsoid inside that goes through the core of the vortex. And the question is how much water would be in that? Well, it must have something to do with the amount of water shoved out of the piston. So if you make the amount of water in a piston, just fill that inner ellipsoid, you quickly get an expression for, this is the volume of water shoved out of the piston, and this is pi times the radius of the piston squared times the stroke length. And if you make these two things equal, then you get a nice expression for the radius of the ring. And we did a bunch of experiments in which we measured the radius of the ring against the stroke length and got this set of dots and put this formula through it. And the best fit gives you an eccentricity of about 0.59 plus or minus 0.05, and direct measurements of the bubble give 0.63. So I think it's quite successful, and it's a neat little thing. If nothing else, it's a good correlation in the engineering sense.
So the things that come out aren't circular?
No, they certainly aren't. Not like the electromagnetic analogy. They're definitely ellipsoidal. I guess I don't really know why. I suppose you could think of Bernoulli forces on the core lengthening the thing sideways, but I don't really know. Just a speculation. Now, one of the most mysterious things, especially if you have to teach fluid dynamics, one of the very, very difficult things is to understand what Lord Kelvin means by the impulse. But impulse presumably has the same dimensions as momentum. And so the question is, what is the impulse of a vortex ring in a viscous fluid? That's certainly got to be a first-class question to ask in the lab. And the way, since I don't own a PIV machine of any kind, and PIV won't measure momentum very easily, I thought, well, back in the 19th century when people wanted to characterize bullets, they would tie a bag of sand onto a rope and fire the bullet into the sandbag. The sandbag would sit still for a minute and then go up like that, come back, and they would measure the maximum deflection and deduce the momentum imparted to the sandbag by the bullet. So it occurred to Ian Sullivan and me that maybe the thing to do is to make a physical pendulum, and we decided the way to do it was to take an aluminum plate which was actually 6 by 6 inches on a knife edge bearing here, and fire vortex rings at that physical pendulum, really. Now, of course, the difficulty of that is that the plate is big, the ring is expanding, it's in a viscous fluid, there's added mass, there's all sorts of complications. So is there any simple way to calibrate the pendulum? And the way that Ian decided to do this was to take the vortex gun out, and he put a pendulum bob on the end of a 6-foot string and had a little piece of metal screwed into the bottom of the thing and fired a laser beam at it. And so the next step, well, he had an electromagnetic release so that he could release the ball from different distances from the where the pendulum is going to be. And so the second part then of this is that you fire a laser into the screen. You have a photocell on the other side, and when the bob goes by, you get let's put this guy here, you get an occultation, which you have to correct slightly for diffraction, but you can do that easily. And so you know exactly how fast that bob is going when it reaches the bottom of its swing, which is exactly where it's going to hit the physical pendulum. Is that clear? In other words, if you know the velocity of the bob and you know the mass of the bob, you sure as heck know the momentum of the bob. And that was the idea that Ian had. And so the third part of his experiment is that he puts the gun back in, he now has a calibration of momentum versus deflection for this piece of aluminum, and went ahead and fired vortex rings at it. And what you find, and we did hundreds of these measurements, what you find is that to a very, very close approximation, the momentum of the water in the gun given by the piston, which is nothing other than the mass of the water times the velocity of the piston, is very, very close to the impulse that you measure with this apparatus. So that is you might think there might be. Did you have a question, Mike?
Well, with the bob, that's where you have to worry about added mass, isn't it?
Yes, you do, and I don't quite know, even though I've written a paper recently on added mass, experimental paper, you don't quite know what to do. It turns out that if you say you don't know, the difference between putting added mass in and not is a few percent. So it doesn't change the result very much. But for other places in this business, the added mass is extreme. Let me give you an example of, some people may not know what that old-fashioned expression added mass really is. Added mass was invented by a Frenchman who published a book in 1786 in Paris. His name was Chevalier de Bois. And nobody paid much attention to him, but he understood from experiments on pendulums and water that the mass of the pendulum was increased by the amount of fluid displaced. And that fell on deaf ears, as far as I could tell, until the astronomer Bessel took a great interest in the thing and repeated these experiments of Dubois. And he made Dubois very, very famous. And the application for us quantum fluids people is very spectacular. If you work with ions and superfluid helium, the positive ion is just an ion, but the negative ion is a bubble about 36 angstroms in diameter. And the only thing in that bubble is an electron, a free electron. And you can think that the wave function of the electron is being balanced by the surface tension of the superfluid around it. And what you find is that thing has a mass, an added mass. I mean, the physical mass is the mass of an electron, which is almost nothing. But the added mass of the bubble is about 350 atomic helium masses. So it's a huge, huge effect in that particular branch of physics.
I guess it's small in your experiment. It must be because the bob is made of a very dense material.
It is. The bob's lead.
If it were the same as water, you'd have, I don't know, factor 3/2 or something like that.
Oh, you'd have a nasty little question. I suppose we could settle that, but I felt since the difference was too small, there's all sorts of other errors in this kind of a measurement. After all, this is pretty crude. This is sort of 19th century physics that I'm doing here.
This is the mass of the fluid that's been dragged along with.
Well, what added mass really is, I think, is the fact that when you move something, start to accelerate something, you've got to push a lot of fluid around.
Right.
The thing that I should have thought was that the added mass would be the same for an inviscid fluid and a viscous fluid. And when I did a sphere, I got the amount of fluid displaced, the factor that is supposed to be a half the mass of the fluid displaced. That's Bessel's expression. That's called K. And if you've got a cylinder, K is 1. Well, I did it as carefully as I could with modern electronics, and I got an added mass of 0.65 instead of 0.5, and that's exactly what Chevalier de Bois got in 1767. So I felt kind of crestfallen. It sent me running up to see Jim Riley to see if we could figure out what the heck was going on. On the other hand, when we did a cylinder, which should have a K of 1, we got 0.95, which was quite splendid.
Okay, which I take it that means you're using small displacement, so the viscous wake has little chance to develop, because of course those formulae are for inviscid irrotational flow, and in which case the 0.5 and the 0.1 are perfectly precise.
Sure. Yeah, it's got to be small amplitude. There's all sorts of complicated things occur, and even a simple pendulum at large amplitudes. For instance, I might have a chance at the end of this lecture to just mention some stuff I've been doing about vortex rings from a pendulum.
Okay, but the question about this is now, how many pendulum diameters does the pendulum get?
Oh, about half a diameter.
How many?
very small, about half a diameter.
Okay, that's why the inviscid theory works fairly well then.
Yeah,
Okay.
but I still think I've made a blunder of some kind in these measurements, and I need to talk to wiser people than me about how to improve things. But it's well, I don't want to dwell too long on this. The difference in predictions is a few percent, so it doesn't matter very much for what we're trying to do today. So anyhow, what that means is that you can take the mass. You can take the mass of fluid in the piston times the piston velocity is equal to the classical expression for the impulse of an inviscid ring, and the circulation then should be the square of the gun radius times the gun stroke times the velocity of the piston divided by the square of the radius of the ring. And I remind you again that radius of the ring could be either bigger or smaller than the radius of the gun. So finally we end up with the velocity being equal to this expression of Phillips, which can also be written the eccentricity times the velocity of the piston to divide by 3 pi times the log factor. The lambda is just this log factor. So you can also use similar arguments to try to estimate the size of the bubble. And the way that is done is you can say that the mass of the water in the piston times the velocity of the piston must be equal to some mass associated with the bubble and its velocity. But you have to remember the added mass really, really matters now. And since this is not a sphere but an ellipse, I had to search around. I finally found out Loitziansky's book has a lot of values of k worked out. And very approximately for my eccentricity, the Bessel k is 0.65. And so the radius of the ring divided by the radius of the bubble is this simple expression. And so that gives you the radius of the bubble, and it works out quite well. So how well do these formulas work? Well, here was the first big shock that I got in this business, and it really was a shock. We measured the velocity with that gun I showed you with the rack and pinion drive. The velocity of the ring, just at the moment it's finished forming. What I call the velocity of the ring is a fictitious velocity. It's what it would be if the formula for slowing were extrapolated back to 0 time. But of course, what actually happens at the mouth of the gun is very complicated. For one thing, as the water comes out of the gun, it inhales virtually its own mass all over again to make the bubble. The bubble is considerably bigger than the ring. So you have to put this added mass in or you wreck everything. And so I took hundreds of hours of data on this expression, and I got, it should have been, according to this homemade formula, it should have been the ratio of the velocity of the ring to the piston should have been 0.3, and indeed I averaged several hundred measurements and I got 0.3. And I thought, wow. And I actually submitted my paper to JFM. Well, it came back with thunder and lightning from all the referees, as you can imagine. And in the meantime, while the thing was out for review, I decided to make a better piston. Because we could see when we were making these rings that every ring was just a little bit different from the last one. And so in order to get the velocity of the ring, which we needed for slowing experiments, we had to devise camera things to follow one ring along, because if you took another ring, it really was a little bit different. Now, I think you'll see why that's so in just a moment. But anyhow, when I built this Swish-Do Vortex gun, an amazing thing, has a linear motor made over here in England. Has a remarkable characteristics, has a resolution of about 10 microns, and has tremendous force. And so it's a marvelous thing to make vortex rings with. And vortex rings emerge with very, very smooth. They have a velocity divided by the velocity of the piston of 0.63. Very embarrassing. So what I finally decided is there's a really quite wonderful paper by Mamelazzi, who was a very early theorist in Landau's group, and who ended up in Georgia, in Tbilisi. And he's a friend of mine, and we've always sort of admired each other's work, but he wrote a paper showing that if you put Kelvin waves on the core of a quantized vortex line, you'd slow it down. And Carlo Berenghi, who was here last week for your conference, teaches at Newcastle, but is one of my former graduate students. Carlo realized that Mamelazzi and his student had used the local induction approximation for their Kelvin wave, so he decided to do a full-scale Biot-Savart calculation. When he was done, he got exactly the same answer that Mamelazzi got. So he wrote to me and said, Kelvin waves on vortex rings should slow them down. And he says, and in fact, for a quantized vortex ring, the ring can actually stop and even back up. And the reason for that is the tilt of the helical waves on the core has to exceed a certain angle, and the ring will stop dead and even back up. So he asked me to try to find a backing up ring, and I did find a backing up ring, which I'll tell you about at the end of the lecture. So anyhow, the only thing I can say right now is that V upon VP has to be just a figure of merit for the gun. There's no way I can do any better than this. I can't make a perfect gun because there's always going to be some disturbance on the core. So I think what you have to do is build a gun and calibrate the thing and go from there. So now I've mentioned the business of the fact that Kelvin waves can slow a ring. The other question is, forgetting Kelvin waves for the moment, what causes a ring to slow down in water? Well, the first thing you'd think of, I think, would be viscosity. But if you read the literature, nobody ever mentions viscosity as a source of a slowing of a vortex ring. So I decided to take a look at that and see what could be done from just pure experiment. So here is a thing you can do. You can imagine that the core of the ring, if it's thin enough, you could just undo it and pretend it's just a vortex line of length 2 pi r and diameter 2a. And you can define the dimensionless drag coefficient as the drag force, which we are thinking it belongs to viscosity, and normalize it in the usual way for drag coefficients. So that implies then that the drag force is really proportional to the loss of impulse of the ring. And so that immediately gives you a very nice expression, namely the rate of change of circulation is directly proportional to the rate of slowing of the ring, which is a very nice expression. So the question is, how do you study this drag coefficient? Well, you can quickly get an expression for the velocity of the ring. Let's see, I wonder if I wrote that down. No, I don't seem to have it. Let's see. Oh yeah, the velocity of the ring is the velocity of the ring at the gun, e to the minus cx, where c is a drag coefficient. And the velocity is a function of time, is this simple thing. And the drag coefficient, which comes in here, is the drag CDC, the dimensionless drag coefficient, times the radius of the core, times the log factor divided by 2 pi r squared. So how do you do that experimentally? what you do is you fire a ring and you measure where the thing is at what time. And that gives you a series of positions x against time t, which is on the left of this slide. You can then make the best fit using these simple formulae, and you can get the decay of velocity as a function of position, which is exponential. So here is the thing saying that the velocities decay exponentially with distance, and that's I call that the Maxworthy law, because it was first published by Tony Maxworthy many years ago, and I think he was absolutely correct. This is the way the velocity changes as a function of time, and this is what the damping coefficient is. So now the thing is that if this is really a viscous effect, you should be able to scale the drag coefficient on the core as a function of Reynolds number. And in my case, I take the Reynolds number to be the velocity of the ring times the diameter of the core divided by the kinematic viscosity. Of course, there's another Reynolds number. You could take the ratio of circulation to kinematic viscosity. That's another perfectly fine Reynolds number too. But here, since we think this has something to do with friction on the core or possibly friction on the bubble, doesn't make any difference. That's a very useful thing to have. Now, here's the drag coefficient for the one you see in all the textbooks for a circular cylinder in a linear flow. And the X's are experiments done with my old gun with the rack and pinion drive. And you can see that they certainly do decrease with Reynolds number, which is more or less what one would expect. Although there isn't a heck of a lot of information about drag coefficients on rotating cylinders. There's some in Goldstein, and it shows that they are lower than the non-rotating case. But you see we have, in the old gun, a lot of scatter, but we do broadly have a decreasing drag coefficient with Reynolds number. The new gun has much lower drag coefficients, much less scatter. And I think that the reason that you got so much scatter from the old gun is just the whole darn business of Kelvin waves again. The Kelvin waves mean that every time you fire that thing, you got a somewhat different set of waves, just depending on what the phase of the waves were at the time you fired the piston. So I think that's a very difficult problem in fluid mechanics, and I haven't thought very much about it.
You're suggesting the waves are due to irregularities at the edge of the gun.
Yeah, and you know, the gun vibrates when it's fired a little bit. The tank gets surface ripples on it. There's all sorts of crap and corruption going on in these experiments, which we definitely don't like to admit to very much. But the new gun is removed by a vinyl hose several feet away to keep the recoil from the gun from disturbing the experiment. But guess what? The results were worse. And I put the vinyl hose on, and I finally realized the vinyl hose was expanding every time I fired the piston. So I wrapped wire around the vinyl thing, and that got rid of that effect. So, but that's the way experiment goes, of course, all the time. So then the other thing is that if this really is Reynolds scaling, then you should be able to do this experiment changing the viscosity. And I made some glycerol water solutions, which have considerably higher, 2 or 3 times the viscosity of water, and verified that the drag coefficient was a function only of Reynolds number and not of viscosity. So I think that's I think that story is pretty well understood. Then the next thing is, how big is the core? We have Phil's formula, the square root of 4 nu t, but we have this darn funny result that the t involved is only the stroke time and not the total elapsed time. So the first thing is Phil's formula right? Well, it's the square root of 4 nu t, so if you keep the stroke the same and vary the time, let's see where the heck is my, yeah, here's the time going from 50 milliseconds to 160 milliseconds. I kept the stroke the same. This is the observed core radius. This is Phil Safman's. And you see the ratio of them are all pretty well right. On the other hand, if you keep the stroke time the same and vary the stroke length, then the observed size of the ring doesn't change at all. So one concludes, at least I conclude, that Phil's formula is in fact correct. Then another way you could measure it is you could fire a laser beam through the core as it passes, and you can measure the amount of attenuation of light as the thing passes through. And what you find experimentally is that the darkness, if you will, of the trace is really a Gaussian, and the half width at half power of this particular ring is 0.087 centimeters, and Phil's formula gives 0.082 centimeters. So I think that's pretty good evidence that Phil really does have it right, and also good evidence that the time involved is just the stroke time.
Thymol blue profile.
This is thymol blue in the core, yeah.
Right, so that will have a different diffusivity than...
Oh, 6,000 times different. Yeah, you can't use this to study the growth as the ring propagates across the tank at all. I'll show you in a minute just how you do that. I've done it. So anyhow, the unfortunate thing is that I can't think of any way to relate the darkening of the, due to thymol blue, to the vorticity. So I can't say anything about what the vorticity distribution in the core is. So that's the bad news of these measurements. All right, well now, you're still up against this aggravating problem about the core not growing. And very, very obviously, thymol blue will not work because the Schmidt number, I actually wrote a whole paper on how the thymol blue thing does. I had learned more electrochemistry than I ever wanted to know. Turns out to be fairly hard stuff. And and I got the Schmidt number from experimental measurements with my own theory, and it is 6,000. So what I did then is resort to something called kaleidoscope. And kaleidoscope is a solution of fish flakes. And fish flakes are used in an American company in the Hudson River Valley making sparkling women's makeup. And the fish flakes and various kinds of paste make sparkling makeup for pretty ladies. And but a chap in Boston realized that it would make a wonderful tracer for fluid mechanics. And the fish flakes turned out to be almost ideal because they're virtually neutrally buoyant. And we used to use, for the previous 20 years, us Taylor Coetters, we would use aluminum paint powder, which will do the same thing. It's also flakes. And I first realized that it would be useful because I built an observatory and we coated the roof of the observatory with aluminum pigment paint, and that keeps all sorts of heat off your telescope during the day. In the business of having the aluminum powder around, we tried it in fluid mechanics experiments. It's wonderful. And for Taylor Coetters, it shows very, very clearly where regions in these Taylor vortex cells, they go through all sorts of evolutions as you increase the Taylor number. You have cells, then you have wavy cells, and then you have all sorts of bifurcations going on. And you can photograph all those things, and Harry Switty has done that at Texas. And it's a wonderful thing. But you see, the kaleidoscope is everywhere in the tank. It doesn't have to diffuse to mark the flow. We don't know what the relationship is between the tilting of the flakes and the vorticity, but we do know that experiments in Taylor Coett flow tell you that where the vorticity is more intense, you'll get more reflection from kaleidoscope. So we went ahead and put kaleidoscope in the tank and did a set of measurements of the apparent size of the core to Safman's formula, and here it is as a function of time for 3 different stroke times, quite a bit different from 0.167 to 1 second. And you can see that really the core does not grow. Now, when I wrote our JFM paper, the statement in the paper is that the core doesn't diffuse. And I had a very nice meeting with Tony Leonard and Tim Nichols last week. And we talked about this, and we sort of decided that it was a silly thing to say. What we observe, this is what experimentalists need to learn at their mother's knee, is you've got to tell people what you observe, not what you think is happening.
Yeah.
So I think what's happening is that the core is diffusing, but after all, we do know that vorticity is disappearing from the core, and I think what's happening is that the stuff that is diffusing is being washed out behind the bubble, and we can see it disappearing as the ring slows down. I wish I'd discovered that, but it was in fact very clearly stated by Crutch in 1939. So I think the open question now that we need to get to is, why in heaven is the rate of washing away of the vorticity such that the core looks to be the same size all the time? And I have no clue whatsoever why that's so. So the conclusion of all this stuff is that we now have a method of making vortex guns of very, very good quality, vortex rings of very, very good quality. And we know exactly what their characteristics will be by setting the stroke length and the stroke time. So now we can do sort of nuclear physics experiments. And I've constructed a big tank, a big circular tank, and I have 2 guns on it. I'm an old, like everybody else my age, I'm an old nuclear physicist, of course, retreaded, like Tony Leonard, both escapees from nuclear physics. And we're able now to make rings of known quality in a viscous fluid and discuss their interaction. And I'd like to show you the kind of nice stuff that you can get from that. Here we have got 2 guns at an angle of about 30 degrees, and they're firing rings simultaneously into the same size. You can see these rings are approaching each other. They are touching each other, and you immediately create an intermediate state in which you've got a compound ring made up of the old ring, both the old rings, and it becomes very unstable, becomes essentially a sort of a figure 8, and fissions. And so the rings are coming in this way, but their products are going up. So obviously this is a very rich field of study, and we'll be able to do this with a lot of knowledge of exactly how to make these rings and how they behave. And there's a wonderful paper by Tim Nichols, who's here in the engineering school, in which he's able to show that half the fluid from each incoming core is present in the exit, in each of the exit rings. So you see, you can offset the rings, you can make them different strengths, different circulations. You should be able to study reconnections. And so I think there's a very large branch of laminar fluid mechanics that can be reached, and also turbulent. It isn't hard to make these rings turbulent, just make them faster, and they'll certainly get turbulent. I think there's a lot to learn, and but at any rate, it's kept us amused. Thank you very much. Mike?
While that picture's up, I ought to mention some wonderful experiments by Kanbei in Japan. I think he's at Kyoto, but I'm not sure. Kanbei done what? Tokyo, I beg his pardon. Anyway, did experiments like that in a gas, and actually managed to measure the sound emitted, which is an extraordinarily difficult thing to do.
Yes.
Well, you have to use much higher Mach numbers than you have.
Oh gosh, yes.
There, but still it's very weak, the emission, as light hill theory leads us to expect. So he's got this incredible gating with these shock tubes. He's his gun of shock tubes. He goes bang, and then suddenly he's got to listen for this tiny sound coming off.
Yeah, I've read those papers. It's
Okay.
marvelous. There's a lot of absolutely marvelous Japanese papers on vortex rings. They really were the pioneers in a lot of the modern stuff. And I hope to meet them all eventually.
But you're saying you've got better control of the fine detail of the rings now, the A values and so on. That's
Oh yeah, we know how big the core is. We know exactly what viscosity does. We're in great shape, and there should be lots of fun. And I think the reconnection studies. One thing I wish we had as a way to generate vortex lines. When Klaus Schwartz was my student, his PhD thesis was to fire quantized vortex rings at quantized vortex lines. And we made the quantized vortex rings the usual way with ions. We made quantized vortex lines by rotating the entire cryostat. So Klaus had an apparatus weighing a couple of tons, rotating around and firing vortex rings. And what he observed was that the cross-section for scattering was exactly the diameter of the ring. And that's what got him interested in doing quantum vortex dynamics, and that's what's led to this whole Schwartz method of doing turbulence by simulation, numerical simulation, which has turned out to be very successful. Yeah, Mike?
So that statement about cross-section means if your ring just misses the line, it actually doesn't interact.
That's correct.
Amazing. You'd think it would if it just
Oh,
grazed.
you would. Oh, yeah. Well, it's not what we expected. And we got these results. We're all sitting around, our bare faces hanging out, so to speak, because we didn't know what to do. You get pleasant surprises like that in physics every now and again.
It's telling you that the quantum vortex core is a highly robust, coherent structure, isn't it? It can hang together with that amount of disturbance.
Yeah, but the minute they touch, they reconnect. There's a nice study of them based on the Schwartz method essentially declares a reconnection. When the cores cross, he declares the topology change. Okay, but it could actually be calculated by using a nonlinear Schrodinger equation, and that's being done by Kochlik and Levine, and they really are able to study the details of reconnection without any ad hoc approximations.
Right. The Gross-Petaevsky equation.
Yes,
Yeah.
that's
Making
exactly
a lot
right.
of assumptions in that statement.
Well, it's a slightly simplified model of the core, isn't it? Nevertheless, one has a feeling it has a certain robustness. Does it check against experiment?
Well, the Kelvin waves on these things are tremendous.
Yeah.
You see, the other thing I haven't tried to talk about, but probably should have maybe in this conference, is our experiments on quantum turbulence. If you know the laws of quantum vortices and do lots of calculations about them, try to understand details of how they work, you would darn fast decide that turbulence in such a thing is going to be vastly, vastly different than turbulence in water or air. And that is exactly wrong. I did that experiment myself with a couple of good students, and what you find is that the decay as a function of time of the vorticity, which you can measure by second sound attenuation, believe it or not, very accurately. 6 orders of magnitude you can resolve. In fact, I once was amused to calculate if I tried to do an experiment like that in a wind tunnel, how big would the wind tunnel have to be? It'd have to be 1,000 kilometers long and 1,000 kilometers high. But we're doing it in something 40 centimeters long. And the decay is essentially classical. And so the good people that are doing all this stuff with vortex turbulence, superfluid turbulence, are trying all sorts of things. One of which was talked about here at the conference just the first of the month. And Carlo Berenghe was here, and he showed some results in which he bundles together a bunch of vortex filaments. And they, of course, will stretch because they can get closer to each other. And will they reconnect? Yes, the numerical simulations show that bundles of quantum vortex lines with maybe 30 or 40 vortex lines in them will in fact reconnect. So it's all very exciting, but part of the problem that we have is what happens when you get below 1 degree. What you find is that not only is quantum turbulence very, very much like classical turbulence above 1 degree, but if you go below 1 degree and say, okay, there's no viscosity left. Okay, if you're at 40 milledegrees, there's really no normal fluid left in helium-2. So you say turbulence should never decay. Well, guess what? It decays just as fast as it did above 1 degree. And so the question is, what the heck is going on?
Hasn't that got to be sound emission?
Yeah. I think what's happening is it's making these...
Anywhere else the energy?
Yeah, I think it's making Kelvin waves, and the Kelvin waves are emitting Bremsstrahl in this.
No, that's not what's going on.
In terms of phonons.
It is sound waves, yeah. But what it is Carlo's calculations indicate that what happens is you get something analogous, but not exactly analogous to a Roberts-Jones soliton that forms first. These are dark solitons. They break down into refraction, which turns into sound waves. But his calculations aren't high enough resolution and other things to really pin this down. But that seems to be the mechanism that happens. The Kelvin waves don't play a role from my point of view and Carlo's point of view in the dissipation of the kinetic energy from the gross Pitiovsky. There are Kelvin waves there, but they're not involved in the dissipation.
Well, Joe thought, the last time I talked to Joe about it, he thought that it wouldn't be Kelvin waves excited by the ordinary things that excite Kelvin waves, but only Kelvin waves coming from a reconnection, where you got a very, very sharp kink.
That's the point of my vortex calculations, is to show that the reconnection involves wave dynamics, but it doesn't generate Kelvin waves on the vortex lines. It forces the energy that's associated with the interaction energy between the two vortices into this very small volume. And what happens to exactly convert it into sound waves is not clear. They're waves that form on the vortices, and Carlo's simulations see these waves that form on the vortices, but my vortex calculations show that those waves aren't propagating outwards, they're actually propagating inwards.
Huh.
And Carlo just gets the stuff right on the outside. You don't see the stuff propagating out from that region. What you see in his latest calculations is all these little vortex rings popping off from this thing.
Huh.
Okay?
It's amazing, but it might bear on what Srinivasan was saying about the reconnection process being to some degree time reversible, remember? Except it isn't quite, because you're popping off your vortex rings. That's
Exactly.
irreversible.
Carlo's calculations conserve energy, the energy of the gross Pitiovsky, okay, to a high degree of accuracy. But the amount of energy that's left in the vortex lines at the end of his calculation is, I think it was like 60% of what was there originally. But the overall calculation still has the original energy. And all the excess energy that was in these original vortex lines that were like this, that's gotten turned into this, all that excess vortex energy has gone out in these rings that turned into refraction waves that turned into sound waves.
Okay, so the rings become solitons and then sound waves.
That's what he thinks is going on. I mean, this is ongoing research.
But some processes, I mean, for example, the one I know, because various people have discovered it at various times. If you look at this classical problem, you take a vortex line and displace it from the center so that you get the second mode, the massive mode of a vortex line vibration. There it's damped very quickly within
classical
gross
vortex line.
Pitiovsky.
Or gross Pitiovsky.
Gross Pitiovsky conserved circulation,
Yes.
but I mean there's a second massive mode, and that's very strongly damped, and it's damped because sound waves go out from this displaced structure, and I can quote a whole lot of papers which have discovered that independently.
Okay, that's a phenomenon I didn't know about.
The massive
Yeah,
mode means the line is displaced bodily. It's wave one azimuthally and long axial wavelength. Is that this massive mode?
Yeah, I mean, it's just the zero. Yeah, it's the second mode of the Bogly-Buff equations, basically.
So the azimuthal wave number is wave one, is it? It says it's wave one azimuthally, so the line is locally just displacing itself. But there must be an axial wave number like that.
No, the wave number can go to zero. I mean, this
The
is something
axial
which
wave-
is in Lamb's hydrodynamics. It's been known for a while, certainly in Russ's
But
book.
be explicit. Which way? You're talking axial or azimuthal wave number? Here's my vortex line. Axial would mean it.
It's the axial wave number is zero.
So the whole line.
I only
from-
know how to do two-dimensional physics.
So the whole line from minus to plus.
The whole line is displaced from the center of symmetry, and there's a classical mode which it just rotates with finite frequency. That mode,
wave
You've
two,
mixed up
is it
something.
Kirchhoff
You're talking
vortex?
about Lamb's hydrodynamics. What we've been talking about here is Gross-Pidiaski. Those are, one's classical, one's quantum. I mean, they're two sets of equations.
sure, but
Some resemblance, isn't there? I mean, are you talking
Well,
about azimuthal
there
wave
are.
number?
if you work on one, you have to know the other.
Azimuthal
That's
wave number
absolutely
two. That's what you're talking about. Azimuthal wave number two, I think. So you're
Yes.
distorting
Yeah, I mean,
the chords.
it's
becomes-
the one which is finite frequency in the limit of zero wavelength and zero axial
Is
wavelength.
this
Okay,
a
that's-
vibration that's associated with the coarse diameter not being circular?
yeah, elliptical cross section.
Okay, well then we have a problem.
No, I'm sorry. Don't know what it's associated. People have done this calculation, a number of different groups over the last 10 years without knowing what other people have done, and they've come out with the same answer, which is it's very strongly doubted.
Well, I mean, okay, so.
Because it radiates further.
It doesn't get round once.
We need to know who's doing this, and we can download the papers.
Sure, I can.
But the other point is, what you're talking about isn't Kelvin waves. Whatever it
No,
is,
no.
it's not Kelvin
No,
waves.
it's the other mode.
Yeah, and that I mean, if such a mode exists, I wouldn't deny that could be a very strong contributor.
But if you start trying to distort it, it will get excited, and what's excited will propagate out in the form of sound waves.
Sure.
So these are phonons that get away from the vortex line.
Yeah.
I mean, there's a
Well,
problem.
everything Gross-Pidiaski. I mean, these are the.
It's quite clear from Carlo's calculations that these vortex rings, these dark solitons that initially come out, aren't stable. And he doesn't have an explanation of why they're unstable. It could very well be.
Maybe he should read these papers.
Could very well
I
be
can give
this
you the name of
mechanism.
3 or 4 different authors who found
These
this.
vortex rings must be very small. They must have a diameter comparable to the, the healing
Absolutely,
length.
yes, they must have a diameter.
That's how they manage to turn into solitons, isn't it?
Right, yeah.
Okay.
Well, I think it's quite
We'll have
amazing.
Paul Roberts here, by the way, in 2 days, so we can
Oh, yeah.
pester him with all these questions.
He and I worked together for some 17 years. We were trying to do theory of this stuff, and it's an awful lot of fun. I hope that you guys in the turbulence business will realize that those of us who are stupid enough to work on quantum turbulence are having a ton of fun. I've been in this business since the early 1950s, and if you tried to have a conference on this subject 30 years ago, you'd get maybe 3 or 4 people come. But at LT25 this summer in Amsterdam, we had about 250 people at the quantum turbulence, all arguing, yelling at each other. It was lots of fun. Times have changed. Well, thank you very much,
Can
ladies
you
and
show us
gentlemen.
the rest of your video?
4:30.
Have it passed?
So,
Okay.